My friends,
What?
we are going to just take on the last day of this chapter. Man, it's so nice to have all these sleep-in days and early release days, but now it's the night before the quiz, and maybe we've started chapter 14 problems, and there's a slew of them, and they're not nice or fun. So I bid you a good evening tonight. So yeah, you know, our Netflix binge is going to just have to wait one day. How about that?
It's going to be 2 weeks until after.
Yeah. All right, well, there's a couple of things I really would not just like, but I need to show you what to do. Things that I skipped over, and my conscience is getting me saying, I don't think I should be skipping these things. So one of the things that I have skipped, if you've done any of the problems in chapter 14, is about the percent dissociation. This is a way, now when we have an acid or base solution, one of the things that we can do with it or measure about it is pH. So we find the hydrogen concentration, take the negative log of it, and that kind of gives some information about the solution. Well, another thing that we can do with a value of initial concentration of weak acid is to find its percent dissociation. Now in this slide, I just give you the formula for percent dissociation. It's this. And it's not difficult at all. In fact, when we do the problem, if you don't see it already, it will look exactly like a calculation that we already do. Can you tell by looking at the formula what percent dissociation is, what calculation is it?
It's like the same composition or something.
No. Now, no. Yeah?
It's the E of the thing.
It's the E. What do you mean the E?
Right? What do you say? What is E stand for?
E. I can't think of what E are.
No, because, okay, so it's the concentration of, like, it's very, you know the E, like, the E is like ICE, E.
Oh, yes. I didn't know what E you were talking about. It is. Yep. Okay, so I'm going to just put that on hold for a moment. The percent, so any percent in general is when you take the part divided by the whole. That's the way I always describe percent. So when you have percent composition, you're looking at the mass of one of the elements in a compound divided by the whole mass of the compound. That's percent composition. Percent dissociation is, okay, when you start with a certain concentration of an acid or base, how much of it dissociates. Let's say that we started with 0.5 molarity of our acid and 0.1 molarity of it dissociated. What would be the percent dissociation? If we start with 0.5 and 0.1 molarity dissociates, it would be 20%. 0.1 divided by 0.5, which would be 20%. So I'm going to I'll walk you through how to do the calculation. It's really very simple. When you ask for the percent dissociation, set up an ice table if it's a weak acid or base. If it's not a weak acid or base, that means it's strong, and that's very easy because they always dissociate 100%. Weaks won't dissociate 100%, not even close, in fact. You'll see. When this thing is dissociating, it's going to go down by some amount x from what it was originally. That means these sides over here, this side, is going to go up by x. And we'll have 0.5 minus x over on the left, x and x on the right. Now, if we want the percent dissociation, we need the hydrogen ion concentration. That's this number right there. We also would use a hydrogen to calculate the pH. But the question didn't ask us for the pH, it just asked us for the percent dissociation. So we'll still have to solve for x. So how are we going to solve for x? We have to use the K value. Right. Now, this is acetic acid. We use acetic acid a lot in this class, so much that I have the value memorized. If I didn't have it memorized, I'd have to go to the book, look up on page 822 on the Ka table. But I'll just tell you that the Ka of acetic acid is 1.8 times 10 to the negative fifth is the K. So when you're looking back at this and you think, how did you come up with that? Well, that's how I got it. It's in the table. So that K value is the same as the ratio of the products over the reactants. So it's x squared over 0.5 minus x. Now I'm going to assume the 5% rule on this one, just neglect that minus x term. So that'll save us the trouble of the quadratic formula. Just take your K is equal to x squared over 0.5, multiply the K by 0.5, and then take the square root. If you have a calculator, would you crank this out and just yell out what you get for, just not the final answer, just what is x? 0.0030?
No. Yeah.
Thank you. And that is, remember what x is. X is the concentration of hydrogen ion at equilibrium, and we get 0.0030. Now, if it asks for the pH, we just take that value and find the negative log of it. But it's not. It's asking us for the percent dissociation. So, I'm just going to extend this. Oh, oops, I didn't mean to do that twice. Well, that was really small. The percent is 0.003 over, I'm just following this calculation right here, the hydrogen ion concentration divided by the original acid concentration, 0.5. So, and that really is what happens because x is 0.003. That means that x was 0.003. So this concentration went from 0.5 down to 0.47. No, to 0.497.
Yeah.
That's right, yeah, 0.497. Because, yeah, that minus that gives, so it just dissociated a tiny little bit. Multiplied by 100. And what is the percent dissociation? That divided by that times 100, it's like 0.6%, right? Now I'm going to ask you again. When you calculate the percent dissociation, does this look like something else that we've calculated in here? What is it, Claire?
Like the 5%.
Well, we want to check the 5% rule. Yeah. It's the same exact calculation as checking the 5% rule. Daniel?
Percent, never mind. I know what you're saying, but I don't forget what it's called.
Okay.
Yeah, never mind. Just don't listen.
Okay. But when you see how I took that 0.5 minus x in the denominator and I neglected the x part to make our math simpler? That means that when we're done, we have a value for x, we're supposed to take that x value and divide by the original acid's concentration. This just gives it a different name. It's the same exact calculation, the same thing. Really, that is what the 5% rule says. It says that if x, the hydrogen concentration, is less than 5% of what the original concentration was, then that means that that the x is sufficiently small to be able to neglect it out of it. Matthew?
Isn't it like 60%?
No, this divided by this gives us 0.006. And then we multiply it by 100. So it was multiplied by 100 to get this number.
0.6.
Did you calculate?
Yeah.
Do it again. 0.003 divided by 0.5.
What isn't it?
0.6.
0.6%.
So that's the percent?
Yeah, 0.6%.
Oh,
Yeah.
Oh, I see now. Okay.
No, it's not.
It's right.
Okay.
Anything else about this? Now, I'm not even going to do another calculation or example with percent dissociation because it's very easy. They don't get hard. Percent dissociation, when you see that the question asks for that, you think, good, I could do this. This is easy. Okay? Set up a nice table, use the K value, solve for X. The next thing is, I left a note for myself. I want to make sure that I get it. Well, it's our last day out. I don't want to leave anything out. Because if I leave stuff out, then I feel guilty, like saying, okay, don't do this problem, don't do this problem. I don't want to have to do that too.
Oh.
All right.
So you can forget.
Oh, no, I insist. I'm going to land on this page just for a moment. I do want to at least introduce you to a term that sometimes will be used, and I think it's worth just at least considering this. The term is amphoteric. Any substance that's amphoteric means that it can act as an acid and it can act like a base. It can be either an acid or a base.
That's terrible.
Kind of cool.
That's terrible.
What's terrible about it?
No, because it's just more stuff.
Wait,
It's cool.
so the H3O, is that the iron?
No, when we're looking at the reactants is where we determine what's an acid and what's a base. Now what do we see happening here? I could have put two H2O in the reactants, but I chose not to for a specific reason. I want to show you that one of these two water molecules is acting like an acid, the other one's acting like a base. This water molecule is giving a hydrogen ion from itself to the other water molecule on the left. So this one, because it's losing a hydrogen ion, it's an acid. This one is gaining the hydrogen ion, that makes that a base. Two different molecules of the same substance, one being an acid and one's being a base. Yeah?
So if you had like water, some of it could be like acid, or would it already go through the reaction?
It depends on what's in it. If you put a base into water, then all the water molecules are going to act like acid. But if you put an acid into water, then all the water molecules are going to act like base by taking a hydrogen from the acid. So it just depends on what is in the water. It's not like when you have neutral water, when you have a sample of just water molecules, a few are going to do that. This is where we get our KW expression. This is the autoionization of water. It's not like it has a difficult time making up its mind what it's going to be. It's not having an identity crisis, I guess. It's just depending on what's in it, it can be either one. Now, not all substances can be either one. HCl is always an acid. It's not able to take a hydrogen ion. But water can be either one. Now, I did want to mention, too, that when a hydrogen ion leaves an acid, any acid, the hydrogen ion doesn't just float around in the water. It's not by itself, ever. And as soon as it leaves the acid, it's always going to get gobbled up by a water molecule to make the hydronium ion. And I just want you to know that. If you go on and take another chemistry class in college, you may have a professor that makes a really big deal out of the fact that hydrogen ions, this term right here, doesn't really exist. The hydrogen is not free. When you have an acid that's giving off hydrogen, this hydrogen ion has to get attached to a water. It doesn't just go free. So it makes the hydronium ion. And that I had professors when I was in my chemistry program, they would be offended if you put H+. They'd get mad at you. Seriously, like you kicked their dog or something. I mean, for some people, it's a really, really big deal. Now, the Zoom dolls, I love the Zoom dolls. They just make things easy, and I don't know how they really, feel in their inner being, but they allow us to just call the hydrogen ion H+ and be done with it. But yeah, if you take some chemistry, you may run into people that really do not like that. They're offended. Okay, now I would just mention too that another example of something that can be amphoteric, just so we have another example other than water, is this thing. This is the bicarbonate, also known as hydrogen carbonate ion. It's amphoteric. If it's around an acid, it can act like a base. So like in water, as a base, this thing would, remember what the job of a base is, it's accepting a hydrogen. So it can act like that and pull a hydrogen off of water to make H2CO3 and hydroxide. Sorry about my writing. I just don't know very well how to write on it. That's a 3, and that's OH negative. The bicarbonate ion can also do this, though. Same stuff. It's still HCO3 negative. It has a hydrogen that it can release. So it can act like an acid. I don't know what just happened. That was weird. I didn't do anything, but I got a red 2. So yeah, this thing, it has a hydrogen that it can release, but it also can take a hydrogen as amphoteric.